infrared region of the electromagnetic spectrum. Here on the top left, I have a picture of the electromagnetic spectrum. You can see that it includes everything from radio waves to microwaves to visible light to X-rays. And these go, as they go across from the left to the right, you see that the wavelength decreases and the energy increases. So my research focuses on the visible and the infrared there in the middle. Visible light is what we see, the color, everything you see that our eyes are capable of perceiving. Infrared is just below that in terms of energy, and the infrared is very important because it's thermal radiation. Thermal radiation, it has a lot of applications in terms of night vision goggles and target identification, as well as gas identification. So if you're trying to see if there's a toxic or explosive gas, then that can be seen with spectroscopy that takes advantage of the infrared spectrum. Another application is the solar cells. Solar cells, 49% of the energy that comes to Earth from the sun comes in the form of infrared radiation, and if we can harness that, it will go a long way towards helping with our energy crisis. So here on the bottom left, you can see that we need to find something that has the correct energy gap. So if you think about the semiconductor energy gap as similar to that of an atomic orbital, you have excited and ground states. So how are we going to do this? We're going to use molecular beam epitaxy. MBE is essentially spray paints atoms at very high purities under high vacuum conditions onto a lattice that we can create with very high precision. And usually quantum dots, which are what we create using the molecular beam epitaxy system, are in the emitter absorbed in the visible range. But when we lower the energy using tensile strain, they then emitter absorb in the infrared range. So tensile strain is when you take a small atom and you put it in a place that's a little bit too big for it. So it's not able to fit quite right, and the process of doing that lowers the lowers the energy into the infrared. So down here on the bottom right, I have a picture of some quantum dots. You can see they're extremely tiny, on the order of 20 to 30 nanometers, which is why they exhibit some different properties than if they were somewhat larger. And this technology and knowledge has only been available to make quantum dots in this way for a few years, and since it's recently available, we'll be able to create materials that are new and exciting, and I hope that you will soon see the applications of our research. Thank you.